A hollow shaft subjected to pure torque attains a maximum shear stress equal to tau. If the strain energy per unit volume in the shaft is tau square divided by 3 times of g, the ratio of the shaft diameters do by di you have to find out. Already we have developed the expression for shear stress in the case of solid shaft, but this time we have a hollow shaft, and in the case of hollow shaft, the torsion formula is T divided by J tau max. So this time it is tau divided by outer radius. Outer radius is d0 by 2, where d0 is the outer diameter and di is the inner diameter. In this case, we'll get torque will be equal to 2 times of maximum shear, that equal to tau multiplied by J divided by d0. Strain energy due to torsion is given as U is equal to 1 by 2 multiplied by T square multiplied by L divided by polar moment of inertia J divided by G. So let's substitute here. T is equal to 2 times of tau into J divided by d0. So we get a strain energy equal to 1 by 2 into tau square. Tau square is same as 4 multiplied by tau square multiplied by J square multiplied by L, and in the denominator we have d0 square and is further divided by J and is further divided by G. So one of the J will be get cancelled. We left here with 1 J in the numerator. This 2 is also get cancelled and we have 2. So we get a strain energy equal to 2 times of the shear stress square multiplied by J multiplied by L divided by d0 square multiplied by G. Now once we know the strain energy, we can calculate the strain energy per unit volume by dividing by volume, which is area multiplied by L, and that value is known to us. So strain energy per unit volume is U divided by V is same as the strain energy density, that equal to U will be equal to 2 times of tau square multiplied by polar moment of inertia J multiplied by L divided by d0 square divided by G divided by volume is area multiplied by length L. So this time the length is get cancelled. Strain energy per unit volume is given as tau square divided by 3 times of modulus of G is equal to 2 times of tau square divided by G. I will write first. Then we have d0 square. So we have d0 square. Then we have to write down polar moment of inertia. Polar moment of inertia is pi divided by 32 into do to the power 4 minus di to the power 4 is further divided by area, that equal to pi by 4. So 4 will shift in numerator. Outside diameter square minus inside diameter square. So this time tau square is get cancelled with tau square. G is cancelled with G. We have 2. 2 into 4 is 8. 8 and 32. So 2 is cancelled. 4 is cancelled. And here 32 by 8, that will be 4. Pi is also get cancelled. On the left hand side we have 1 by 3. Now do to the power 4 minus di to the power 4 can be written as do square plus di square into do square minus di square is further divided by d0 square. So this term will divide by d0 square, and this term will write here, that is d0 square minus di square, and this 4 is left, that equal to 4 do square. So d0 square and d0 square minus di square is get cancelled. We get here 4 by 3. do square by do square equal to 1 plus we have di by do whole square. So in this case we'll get di by do whole square equal to 4 by 3 minus 1. 4 by 3 minus 1, that will be same as equal to 1 by 3. So finally, if you take under root, I will get this value as di divided by do is equal to 1 by root 3, or we have do divided by di is equal to root 3. A uniform torsion rod is subjected to distributed torque equal to T0, that is the torque per unit length. Derive an expression for the total strain energy stored in the rod. Express your answer in terms of T0, diameter T, length L, and the shear modulus equal to G. So we have given here one uniform cross-sectional shaft of length equal to M and subjected to torque per unit length. Since here the torque is variable, you have to use the method of integration. And we'll set the x-axis as a longitudinal axis here. At fixed end, we have x equal to 0, and at free end, we have x is equal to L. From the origin, we'll take here a section at a distance equal to x. So we'll consider this section, and for this section, we'll find out the strain energy first. So this section we have taken outside. This section from the origin at a distance equal to x. Total length is equal to L. So we have length of the given section is L minus x. This torque is acting in a anticlockwise sense, so you have to show here internal torque. So let's represent here the internal torque that equal to Tx, that is the function of x. So Tx represents here the internal torque. For this purpose, to find out the value of Tx here, we'll take the sum of all torque must equal to 0. Now this torque is Tx is positive value. If I consider the clockwise is positive, in that case we have torque at any distance x is equal to, this torque is to be added over the length equal to L minus x. So that is minus of T0 into L minus x. This total sum must equal to 0. So torque at any section Tx will be equal to T0 into L minus x. Since here the torque is a function here, we can calculate here the total strain energy by method of integration. So total strain energy is given as U equal to integral from 0 to L of the torque, which one is a function of x square of it multiplied by dx, and is divided by 2 times of the polar moment of inertia multiplied by modulo of unity g. 2 times of j into g is a constant quantity. Tx square we can replace as T0 into L minus x. So even the T0 is also common. So we have constant is T0 divided by 2 times of polar moment of inertia multiplied by g. And inside the integral sign, which has a limit from 0 to L, we have Tx square is same as equal to L minus x whole square multiplied by dx. Integration of L minus x whole square will be L minus x cube divided by 3, and further we have derivative of L minus x. So we'll get this time we have T0 square divided by 2 times of polar moment of inertia divided by g. Integral will be L minus x cube of it divided by 3. We have derivative of L is 0, derivative of minus x is minus 1, and here we have limit of integration is from 0 to L. So we'll get here minus 3 and 2, that will be minus 6. So we will get here minus of T0 square divided by 6 times of polar moment of inertia divided by g. Upper limit here is L, so L minus L, that will be equal to 0. And second time it is x equal to 0, so that will be equal to L cube. So minus sign will be get cancel here, and in the numerator we will get T0 square multiplied by L cube divided by 6 times of j. So j we can write as pi by 32 d to the power 4. So multiplied by pi, 32 will shift in numerator, d to the power 4. And is further divided by g. Both numerator and denominator here will divided by 2. So we have strain energy will be equal to 16 times T0 square multiplied by L cube is divided by 3 times of pi into g into d to the power 4. A thin walled circular tube and the solid circular bar of the same material are subjected to torsion. The tube and the bar have the same cross-sectional area and the same length. What is the ratio of the strain energy U1 in the tube to the strain energy U2 in the solid bar if the maximum shear stress are the same in both the cases? In this case, we have a thin tube of radius equal to r, thickness equal to t. So we have area which is same for both tube and solid is equal to circumference, which is same as equal to 2 pi r multiplied by t. And in the case of solid bar, the area will be equal to pi and the radius will be equal to r2 square. And these two values are identical for both, that is tube as well as solid bar. U1 represents here the strain energy in the case of tube, and U2 represents the strain energy in the case of solid bar. U1, the strain energy is given as T square multiplied by L divided by 2 times of polar moment of inertia divided by G, that is J1. G is also same. U2 is also given with the same formula, which is equal to T square multiplied by L divided by 2 times of J2 divided by G. For thin tube, we have polar moment of inertia J1 is equal to 2 times of pi into r cube multiplied by t. So we have 2 pi r cube multiplied by t. Whereas the polar moment of inertia for solid shaft is pi by 32 into d to the power 4. D is same as equal to 2 times of r2 to the power 4. 2 to the power 4 is 16. So we have J2 is equal to pi into r2 to the power 4 and is further divided by 2. Value of tau max is same in both cases, and for tube we can write the torsion formula equal to T by J. We have torsion formula is T by J equal to maximum value of shear stress divided by the radius r, which one is the outer radius. So in this case we have torque is equal to tau max multiplied by J, and we have J is equal to 2 pi into r cube multiplied by t and is further divided by r. That is, we have torque is equal to tau max. So we have torque is equal to 2 pi r cube and r. So we have r square multiplied by t multiplied by tau max. And in the case of solid shaft, we have torque is equal to again same formula, that is we have maximum shear multiplied by polar moment of inertia divided by the radius r. This time we have radius equal to r2. So we have tau max, polar moment of inertia is same as pi r2 to the power 4 divided by r2. 1 2 is left from the polar moment of inertia. So we get the torque in the solid shaft equal to tau max into pi r2 to the power 4. One of the r2 will get cancelled. We'll get this value as pi into r2 to the power 3 multiplied by tau max and is divided by 2. Length is remains same, G is also remains same. So we can calculate here the strain energy in the tube using the U1 relation. We have U1 is equal to T square is same as equal to 2 pi into R square multiplied by T multiplied by tau max, and you have to make a square of it multiplied by L. We already 2 here, and then we'll write J1 that equal to 2 pi into R cube multiplied by T and is further divided by G. So you will get here 2 square that equal to 4 into pi square into r to the power 4. We have T square multiplied by tau max square multiplied by length L. In denominator we have 2 into 2 is equal to 4. We have pi, then we have r cube multiplied by T divided by G. Let cancel out common terms here. 4 is cancelled. Pi is also cancelled, so 1 pi is left. R cube is cancelled, 1 r is left. This t is cancelled, so 1 t is left. So you will get U1 is equal to pi RT. So we have pi into R into T multiplied by tau max square of it multiplied by length L is divided by G. Now recall that we have area is equal to 2 pi RT, which is common to both, and this term here is pi into R into T. So we have pi into R into T is same as equal to pi into R into T is A by 2. So finally we'll get here U1 is equal to area multiplied by tau max square of it multiplied by L, and is divided by 2 times of modulus of GT. So we have developed the expression for U1. Now we'll develop the expression for solid bar. So for solid bar we have U2 is equal to torque T2 square. Torque T2 square is same as pi square into R2 to the power 6 multiplied by tau max square is divided by 2, that will be equal to 2 square is 4 multiplied by length L divided by 2 times. So we have divided by 2 times J equal to pi by 2. So we have pi and 2 will shift in numerator. Then we have R2 to the power 4. So we have R2 to the power 4 and is further divided by G. Now this time pi is get cancelled here. This 2 and 2 will cancel here. This R to the power 4. So here we have R2 square. So we get U2 is equal to pi into R2 square multiplied by tau max square multiplied by length L divided by 4 times of G. Now pi into R2 square is same as area A. So area is same again for both the section, that is a tube and solid, and area is equal to pi into R2 square. So this time we have U2 will be equal to area multiplied by tau maximum square multiplied by L divided by 4 times of G. So if you take a ratio here of U1 by U2, so we'll get U1 by U2. Area into tau max square is both is get cancelled, and these 4 will shift in numerator divided by 2, that is this 2. So the required ratio of strain energy is equal to 2. The video you are watching is from the app, which is the Mode Class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.